the shape of their heights, if I make a histogram of those 100 women's heights in my sample, there'll be fewer of them, but it'll look generally the same, right? There'll be a lot of them that are around the middle, a few far out here, right? It would look generally the same. If I have a sample of 100 women, it would still be kind of centered around that 5'5", and I would expect that it might range from somewhere around 4'10" to somewhere around 6 foot. Right? If I sample 100 women from this population and they're representative. Okay? And now suppose that I take the mean height of these women in my sample. Okay? I take the average. So I have these 100 women, and I'm going to get, if I take the mean of their heights, I'm going to get something close to 5'5". It's not going to be exactly 5'5", but I might get a number right there. Okay? All right. And that's the idea. And that's what you have. If you get one data set, you get one sample from the population, it has one sample mean, and you're done. But conceptually, let's think about what we'd expect to see if we erased this sample and started over. What if I put those women back into the population and again drew a sample of 100 women? It wouldn't be exactly the same distribution of heights. It would still look kind of like the population distribution, right? And if I took the average of these new 100 women's heights, I'd get a slightly different mean, right? My sample mean would be a little bit different. Maybe it'd be over there, right? It still wouldn't be exactly equal to the population mean, and it wouldn't be exactly the same as the average heights of the women I drew a moment ago, but it would be around that middle. Okay? And what if I did it again? Okay? What if, again, I thought about sampling? The histograms are going to get less beautiful as we continue this. Okay? And I'm going to get another sample mean. The idea is that if I repeatedly sampled 100 women at random, representatively, from the population, and wrote down the mean of their heights, if I did that, say, 10,000 times, what I would get, let's do it this way. Let me erase this so that it actually looks good. What I'd get would be a distribution of sample means, right? If I repeatedly drew samples from the population and wrote down the mean, and then threw out that sample, drew another sample, wrote down its mean, I'd get a distribution of sample means. I'd expect that distribution of sample means to be centered at the same place as my population. In other words, I'd expect that on average, if I draw 100 women from the population and write down the mean of their heights, on average that mean will be equal to the mean of all women's heights. There's no reason it would be higher or lower. There's no reason that on average the mean of 100 random women's heights would be any bigger or higher, bigger or lower than 5'5". So it should be centered in the same place. But I'd expect the variance to be much smaller. I would expect the variance to be much smaller. In other words, if you draw one woman from the population of adult women in the US and told me her height, I wouldn't be shocked if she turned out to be 4'11", right? There are women who are 4'11". I would not find that shocking. But I would find it shocking if you drew 100 women at random from adult women in the US and took the average, the mean of their heights, and if the mean was 4'11". That would be really surprising. I might think that in general, women's heights range from somewhere around 4'10" to somewhere around 6 foot, but the mean of 100 women's heights should have a much smaller range. Right? That's what I'd expect to see. The variance of the sample mean should be smaller than the variance in the population. And in particular, to start using notation here, suppose we represented the variance of all these heights with the Greek letter sigma squared, and we'll talk more about variance as we move on, but for now, here's a symbol that represents the variability of all these numbers. Okay? That's the variance in the population. Let's say variance of population. Then we'd expect the variance of sample means to be equal to the variance of the original population divided by the sample size. This is the sample size. Let's look at this quantity for a moment.